We're going to look at a type of application problem called related rates. First of all, let's get the idea of what related rates types of questions are. What we're going to do is we're going to find the rates of change of two or more related variables that are changing with respect to time. Some examples are situations where we might see related rates occur if we are comparing the change in volume of a balloon to the change in the radius as we blow up a balloon. If we compare the volume of a tank of water to the height of the water as we drain the tank, or the change in distance between two cars leaving an intersection. Notice everything we're comparing is a change, a rate of change. And that's why we call this related rates. Instead of just looking at a regular equation and relating the variables, we're going to take the derivative and relate the rates together. Here are our steps for solving a related rate problem. Step 1, we're going to picture it. We want to draw a diagram to represent the situation. Step 2, we're going to make a list of everything that we know and make sure we choose clearly defined variable names. If our quantity is a rate, then we need to label it as such, label it as a derivative. And we'll talk about that a little bit more later as we get into the problems. Step 3, what do we want to know? Well, we're going to make a list of all quantities that we need to determine. And again, we're going to choose clearly defined variable names. Step 4, we need to figure out how the variables are related to each other. So we'll find an equation that relates those variables. When we say find an equation, a lot of time this will be a geometric equation or the Pythagorean theorem or something like that. We will find an equation that relates all of it together. Step 5, how are the rates related? We're going to differentiate that equation we just found implicitly with respect to time. And then we'll have an equation that relates all the rates together. And then finally, we'll solve. At the very end, we'll evaluate these derivatives at the point in time that we are asked to care about. All right, let's look at some examples. Example 1, we have a spherical balloon that is being inflated at a constant rate of 20 cubic inches per second. We want to know how fast is the radius of the balloon changing at the instant the balloon's diameter is 12 inches. And then a follow-up question, is the radius changing more rapidly when the diameter is 12 inches or when the diameter is 16 inches? So we'll get started by drawing a picture to visualize what's happening. So we have a balloon, so we'll draw a sphere here. So here's our sphere. The balloon has a radius, r, and what's happening, this balloon is being inflated, so we can think about it as growing out in all directions. So its volume is increasing and its radius is increasing, and we want to see what is happening there. All right, so what do we know? Step 2, what do we know? Well, we have been told that the balloon is being inflated at a constant rate of 20 cubic inches per second. And notice that it says that's a rate. So we know some rate is 20 cubic inches per second. But what is that? Well, it is the inflating of the balloon. That's a volume. So the volume is changing at 20 cubic inches per second. And how can we represent a changing volume? We're going to call that dV dt, the change in volume with respect to time. This is a rate. The 20 is a rate. It is not the volume itself. It is how the volume is changing. Okay. What are we looking for? So what are we looking for? It says how fast is the radius of the balloon changing at the instant the balloon's diameter is 12 inches. Okay. So we'll go back. This was kind of the blue right there. We'll kind of label things as we go. What do we want to know? We want how fast is the radius of the balloon changing. So that's a rate. I'll call it dr dt is my question mark. I'm looking for that rate. When, specifically, what point in time when diameter is 12 inches. Okay. And notice, generally in equations in geometry, we often use radius instead of diameter. So I'm going to go ahead and think about if diameter is 12, that means radius is 6 inches. Remember, your radius is half the diameter. And then the second part says, well, is it changing more rapidly when the diameter is 12 inches or 16 inches? So we also want to know how DRDT is, what DRDT is when the diameter is 16 inches, which means radius is 8 inches. So these are the questions we're trying to answer. We'll label that too. All right, so we figured out what we know and what we want to know. Step 4 is we need an equation that relates the variables together. So we were talking about the volume and the radius. So we need an equation about volume and radius about a sphere. So what we know, and we can look these up on the internet or Google on something and find these equations. But volume of a sphere is V equals 4/3 pi r cubed. And that is our equation. All right, our next step after that, we don't plug anything in yet because we want to find the rates. We want to know how the rates are related. So our next step is we're going to find the derivative and we're going to find it implicitly. So step 5 is derivative. And then just as a reminder, we're going to use implicit differentiation to find this. So let's take the derivative of both sides with respect to t. Remember, we're going to take the derivative implicitly with respect to time. So if we start on the left here, we'll start over here at v and we'll move along. What is the derivative of volume? Well, it's dv dt equals, and now when I see 4/3 and pi, those are just constants, so I'm just going to write them down and let them hang out till later according to the constant multiple rule. And then what's the derivative of r cubed with respect to t? Well, with respect to t, r is a function, so it will be 3r squared dr dt. I'm going to take one more step and clean this up because I notice I have a 3 in the bottom and in the top here. So I can write this a little bit better, and I'll end up with dv dt is 4 pi r squared dr dt. So what I've done is I have related my rates together. I now know how these two rates, the dv dt and the dr dt, are related. So step 6, I can evaluate. So I'll plug in and solve. Okay, so I did have 2 questions, so I'm going to come back up here. We'll do part A and part B. So let's look at part A first. I want dr dt when d is 12, which means r is 6. So when r is 6, at that moment in time, when r is 6 inches, so that is, I'm using my related rates equation down here. I'm just going to plug in from left to right. So dv dt is 20 equals 4 times pi. Now I need r squared, so that's a 6 squared times dr dt. And remember, dr dt is what I'm looking for, so I don't know what that is yet. So I'll just leave it as dr dt and solve for it. All right, so I'll divide both sides by all that stuff next to dr dt. So I get 20 over 4 pi times, well, 6 squared is 36 equals dr dt. And I think this can clean up a little bit because 20 over 4 is 5 over 1. So what do I get? 5 dr dt is 5 over 36 pi is what's left over. And let's take a minute and make sure we know what the units are. This is dr dt. R is measured in inches. So what is happening with respect to time? So it is 5 over 36 pi inches per second is my unit here. All right. So part B, though, says, now what about when R equals 8 inches? So this first one was that snapshot in time when my radius was 6 inches, when that's how big the balloon was. Now the snapshot in time when R is 8 inches, how big is the balloon? So we're going to follow the same kind of pattern. We're going to plug in and solve. So this is still dv dt is 20. 4 and pi are constants. And now I need my radius cubed. So squared, 8 squared times dr dt. And just like last time, I'll solve. So this is 20 over 4 times pi times 64 is dr dt. And just like last time, I can clean up a little bit. And I end up with dr dt is 5 over 64 pi inches per second. So that's how the radius is changing at that instant in time that the radius is 8 inches, is 5 over 64 pi inches per second. And so, which one is the bigger number? Because we saw that last question up there in the directions. Is the radius changing more rapidly at 12 inches or when the diameter is 16 inches? Which one of these is the bigger number? It looks like dr dt is the bigger number. Dr dt for when radius is 6, excuse me. So we are changing more rapidly here. So r changing more rapidly when d is 12. All right, so we've done our first related rates equation, our problem. So let's keep going. Oop, I had a blank page in there. All right, so here's our second example. We have a pebble that is dropped into a pond, and it's causing ripples that are forming concentric circles. The radius of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, so at that snapshot in time, when the radius is 4 feet, what rate is the total area of this disturbed water changing? So step one, we're always going to draw a picture to think about what's going on. So what's happening, you drop a pebble into a pond, and then it's forming these concentric circles, sort of rippling out. So not the most perfect picture here, but this is sort of the idea. These concentric circles are sort of going out. And we have a radius that we need to be aware of because this is circles that we're dealing with. All right, so there's a picture to sort of get our idea wrapped around what's happening. Step two, what do we know? Well, if I look back up here, it says that the radius of the outer ripple is increasing at a constant rate of 1 foot per second. So that tells me that the radius is changing, so that's dr dt is what I want to label that, is increasing at a constant rate of 1 foot per second. So I've translated that over. And then what do I want to know? Let's see what it's asking us. It says when the radius is 4 feet, so at that snapshot in time, at what rate is the total area of the disturbed water changing? So it's asking us, how is area changing? So I'm going to say dA dt, that's how area is changing, that's what I'm going to call it. That's my question mark. And at what is my moment in time? And that's when r is 4 feet. So that lets me know what I'm looking for. I'm looking for how area is changing at the snapshot in time when the radius is 4 feet. So when this pebble is dropped and those concentric circles are getting bigger and bigger and bigger, at the snapshot that we're 4 feet of a radius, what is going on with our area? All right, so our next step is finding the equation. So I need an equation that relates the variables together. So I have radius and area. So I'm going to use area of a circle. And area of a circle is pi r squared. All right, step 5 says find the derivative. We need something that relates these rates together. So if I take the derivative of a equals pi r squared, I'm going to start at the left. So derivative of a, of area, with respect to time is dA dt equals, pi is a constant, so I'm just going to write it down. And then what's the derivative of r squared with respect to t? Well, that would be 2r dr dt. Remember, this is implicit, sort of like that chain rule thing happening. R is a function of t, so you're doing a chain rule, and you have to tag on the derivative of r. All right, I'm going to take one more step. dA dt equals 2 pi r dr dt. No reason except for it just feels better to write 2 pi than pi 2. Either way is fine. All right, so step 6, now I need to plug in and solve. Okay, so how do I plug in and solve? I need to look at my derivative and plug in the rates and things that I know. Okay, so I'm going to start over the left on dAdt. What is dAdt? Oh, well, I don't know that. I'm looking for dAdt, so I'm going to leave it as dAdt. Equals 2 and pi are constants, so I'm just going to leave them alone. What is r? What is my radius? Well, it tells me up here that I want to know the snapshot in time when radius is 4 feet. So r is 4. And then what is dr dt? That is something I know as well. dr dt is 1 foot per second. So I'll put a 1 there. So multiply this out, I end up with 8 pi. So the answer is 8 times pi feet squared per second. And how do I know my units here? Well, it's how area is changing with respect to time. Area would be in square feet, and then respect to time, so per second. Okay. All right. Let's go to another one. All right. Example 3. How rapidly will the fluid level inside a vertical cylindrical tank drop if we pump the fluid out at 3 meters cubed per minute if the tank has a radius of 1 meter? And then a secondary question, what if the radius is 10 meters? Okay, so step 1, let's draw a picture and think about what's going on here. All right, so I want to draw a cylindrical tank. So here's maybe the top and the bottom of my cylinder. And I will make it, there's the walls. Maybe I have, here's my spout right here with my water coming out. And then what's going on, I have some water in it. So let's just say, we have maybe this much water. So we have, our fluid level is kind of right here. This is how much water is in it to start, maybe. So let's assign some variables here. I have the radius of this tank. And as I'm talking about this, I'm talking about the fluid level dropping. So I don't care about how tall the actual cylindrical tank is. I care about where the fluid level is. So I'm going to call this my height. That's the height that I'm concerned with. That's my fluid level. All right, so we sort of have a picture of what's happening here. Step 2, let's figure out what do we know. Okay, so what do we know? If we pump the fluid out at a rate of 3 meters cubed per minute, and we also know that the tank has a radius of 1 meter. And notice that radius doesn't change in this situation. The radius of this tank is always 1 meter. So we know that from the beginning that R has to be 1 no matter what's going on. That's not changing. And then we're pumping the fluid out at a rate of 3 meters cubed per minute. So that's a rate, and that's how the volume is changing because it's the amount of water. So dV dt is 3 meters cubed per minute. And let's think just a minute about how this is going. How is the volume changing? Well, we're pumping it out at 3 meters cubed per minute, but it's going out. So it's actually decreasing. So we're going to define this as negative 3 meters cubed per minute because we're losing 3 meters cubed per minute of water per minute. Okay. All right. So what are we looking for? Well, let's highlight that real quick. What do we want to know? Okay. Let's look back up here. We are being asked how rapidly will the fluid level drop? So that's a rate because it's saying how rapidly will it drop, and it's talking about the fluid level, so that's our H. So we need dH dt is a question mark. And it doesn't have a specific moment in time going on here because that radius isn't changing. So all the moments in time are the same. All right. So let's keep going. Step 4, we need an equation. All right, so we're talking about a cylinder and we've got its volume and its height and a radius. So we're going to use volume of a cylinder as our equation. And we could go look that up, but the volume of a cylinder is pi r squared h. Okay. And one thing to note, we know r is constant in this case. And since r is constant, we could even, we'll have to remember that as we go to the next time, a step later, that we can just leave r as constant. Okay. All right. So let's take our derivative. What is our derivative here? So we'll start on the left. So dv dt equals, well, pi and r squared are both constants. So I'm just going to leave them as pi and r squared. I do not have to do anything to take their derivatives. They are the constant multiple rule, so that they can just be written down and dealt with later. And then what's the derivative of h? Well, the derivative of h is dh dt. Okay. And so now step 6, I can plug in and solve. So if I plug in and solve, dv dt, I know that's -3. That's pi. What is my r? R is 1. That was something we found in step 2. So 1 squared times dh dt. And I don't know that yet. That's what I'm looking for. So we would get, if we divide, we get -3 over pi equals dh dt. But I need some units. How is the height changing? Well, it's in meters. This is measured in meters, and it's per minute. So this is meters per minute. So -3 over pi meters per minute. And the negative makes sense because if we're pumping water out, the fluid level should be going down. Okay, now that was our first question. So that said, that was if the tank has a radius of 1 meter. So this is if r equals 1. What about if r equals 10? Well, we can just jump back in and say -3 equals pi now times 10 squared dh dt. Okay, so that tells me that -3 over 100 pi meters per minute is how my fluid level is changing if this tank were 10 meters in radius. And there we go. Okay, so let's look at this next example. Now we're going to be pouring gravel from possibly a dump truck or something, but gravel is being poured into a conical shaped pile at the rate of 100 feet cubed per minute. The diameter of the base of the cone is approximately 4 times the height. And so we want to know how fast is the height of the pile changing when the height is 10 feet. Okay, so let's draw a picture. So I'm going to draw myself a cone. There we go. So we can think what's happening. Gravel is being, falling down, and it's going to create this cone. Cones have a height that's important and a radius that is important. So there's sort of our diagram to keep up with things. All right, what do we know? Well, what have we been told? So it says that gravel is being poured into a conical pile at the rate of 100 feet cubed per minute. So that's how the volume of the pile is changing. So dv dt is increasing, so we'll keep it positive at 100 cubic feet per minute. Okay. Now let's look and see, what do we want to know? What do we want to know here? It says, how fast is the height changing when the height is 10 feet? So the height changing, so we want to know what is dh dt when at the instant in time that height is 10 feet. Okay, so let's go to our next step. We need an equation to relate these things together. So a useful equation is probably volume of a cone And we could look this up. The volume of a cone is V equals 1/3 pi r squared h. Okay. And so let's kind of examine what's happening here. V is definitely changing during this situation. The volume changes as we add more gravel. Does the radius change as we add more gravel? Well, yeah, because as the gravel goes in, this pile gets bigger and it would get wider and wider and wider the more gravel you add. So R is changing. And is the H changing? Well, yeah, as we add more gravel, the pile gets taller. So we see all of these changing, which is a little bit of an issue because when I come back to what I know and what I want to know, I know things about dV dt. I'm looking for dH dt, but I don't really know how R is changing. So this is where this third little piece of information here in the middle is going to help us figure out some extra things going on. So it says that the diameter of the base of the cone is approximately 4 times the height. It's telling us that that is a constant relationship that's going on here. So what is this saying? It says that diameter is always approximately 4 times the height. I don't really care about diameter. I do care about the radius. So I'm going to say 2 times the radius is 4 times the height. And if you remember, if I look down here, I kind of want to get rid of this R because I don't really know what's going on with it. I need stuff about H's derivative. I know things about V's derivative. I need to get rid of this R. So I'm going to replace it here. I'm going to solve for R. So if I divide by 2, this tells me that R is 2H. And that's a constant relationship that's always going to happen because it's growing with this idea of similar triangles, how the cone is growing. So I can actually come down here and say that V is 1/3 pi, and instead of R, I'm going to say 2H squared H. And I'm going to take a minute to simplify this. So this is V is 1/3 pi. 2H quantity squared will be 4H squared times H. So finally, V is, combine my constants, I'll get 4/3 pi, and then combine my H's, I have H cubed. So for this particular situation, this is the volume equation I'm going to use because I needed to get rid of a variable, and I got rid of the variable R by knowing how R and H were always related throughout the entire time. So we'll label that as green right there so we know where we got that from. All right, so step 5 is we need a derivative. So let's take the derivative here. The derivative of the left, we'll start on the left with V. And remember, I'm looking way down here at the bottom. I'm going to look at this very last one. So I'll have dV dt equals 4/3 pi. Those are both constants. And the derivative of h cubed with respect to t will be 3h squared dh dt. And we'll take a minute and clean this up. I see a 3 on the bottom and on the top. So I'll have dV dt equals 4 pi h squared dh dt. And now I can plug in and solve. Okay, so if I plug in and solve, dV dt is 100 equals 4 pi. What is h? It says when h is 10 feet, that's the moment in time I care about. So I'll plug in a 10 squared, and then I don't know dh dt. That's what I'm looking for. So there's dh dt. So I'll get dh dt by itself by dividing. So it's 100 over 4 pi times 100 equals dh dt. And those hundreds are going to cancel. So I have that dh dt is, I'm left with 1 over 4 pi. And I need to make sure I use some units. So how is this working? Let's see, height was in feet, and everything was talking about per minute. So this will be in feet per minute. All right. So there we go. All right. Let's look at a couple more examples now that involve triangles. So this is a very classic example. So we have a 13-foot ladder that is leaning against the wall of a house, and we're going to take the base of it and pull it away from the wall at a rate of 2 feet per second. And we want to know how fast is the top of the ladder moving down the wall when the base is 5 feet from the wall. And then a follow-up question, what about the base being 12 feet from the wall? So step one, let's draw a picture. So we have a house. Here it is. And then we have, here's our ground here, ground level. And what are we doing? We're leaning a ladder. So here's our ladder. And we know it is a 13-foot ladder. So I'm going to label this as 13 feet. Let's make this a little bit bigger. Yeah, okay, there. I think that'll be a little easier to see. So there's our 13-foot ladder. And what else do we know? Let's see. I see a triangle being formed between the wall of the house and the ground and the ladder. So I'm going to label this part of the triangle as X and this part of the triangle as Y, and let that be my variables. Okay. So let's see, what do we know? Let's see, well, we know that this is a 13-foot ladder, and the size of the ladder doesn't change. This isn't like, it didn't tell us it's one of those, telescoping ladders that gets bigger and smaller. It's just a 13-foot ladder. So we need something to represent that. So let's maybe call that Z. So Z is 13 feet. That makes sense. X, Y, and Z is our pieces there. What else do we know? It says that the base of the ladder is being pulled away from the wall at 2 feet per second. So the base of the ladder, so that's right here, it's being pulled away from the wall. So it's going this way at 2 feet per second, which means this distance X between the base of the wall and the base of the ladder, it is increasing at 2 feet per second. So X is changing, dx dt is 2 feet per second. And it's positive because that distance is getting larger. Okay, so that's what we know. Step 3, what do we want to know? Okay, so let's see, what do we want to know? It says, how fast is the top of the ladder moving down the wall when the base of the ladder is 5 feet from the wall? So how fast is the top of the ladder moving down the wall? So right here, this top of the ladder, as it moves down, we want to know how fast it's going down, which means that's how is y changing, this distance y. So I want to know dy dt is something when the ladder is 5 feet, when the base of the ladder is 5 feet from the wall. So let's think about that. When the base of the ladder is 5 feet from the wall, so that's when x is 5. So what is dy dt when x is 5? And then the secondary question, so that's A. Part B says, what is dy dt when the base is 12 feet? So when x is 12. So we have 2 pieces we're looking for. Okay. All right. So step 4, we need an equation. Okay. Well, I have a triangle, and it's a right triangle, and our favorite theorem ever says that x squared plus y squared is z squared. So our Pythagorean theorem is what we're going to use here. Okay, and let's kind of think through this for just a second. X and y, these change as we go through our problem because the distance from the top of the ladder to the base of the house is going to change as we move the ladder, and so is this. But remember, z is not going to change, right? Z is not going to change because it is a fixed length ladder. So this is constant. And it's just helpful to sort of remember that as we go with this, which tells me, what is the derivative of z? Well, it's going to be 0. Okay. All right. So 5. Step 5, we will find our derivative. Okay. So let's just start on the left. So the derivative of x squared with respect to time will be 2x dx dt. Y squared will be 2y dy dt. And z squared, it's a constant. So remember, this tells me that it's dz dt will be 0. So I can, I can say, well, this is 2z dz dt, but I know this is eventually just going to go to 0 because of that dz dt. Okay. So let's keep going. We can simplify this one little step. I see that everything has a 2 in it, so I can kind of factor that out and on everywhere. So I have x dx dt, oops, not equals, plus y dy dt equals 0. And here I will, to step 6, I can plug in and solve. Okay. So what is x? Oh, let's look at part A first. I'm just going to start at the left. X is 5 at the moment I care about. Dx dt is 2 plus, what is y? Oh, I don't know y. How could I figure it out? So let's think. If I know x is 5 and I know that this is 13, I can use the Pythagorean theorem to solve for y. So 5 squared plus what squared equals 13 squared. So you can do that on your own, but it ends up implying that y is 12. 5, 12, 13 is a triangle. Okay, so y is 12. dy dt I don't know, so I'm going to leave it as dy dt, and this equals 0. All right, so now I just solve for dy dt. So 12 dy dt is negative 10. So dy dt is negative 10 over 12, or negative 5 over 6. And it is feet per second would be that rate. Now, does it make sense that it is negative? Well, yeah, I'm talking about y. How is y changing? If we're pulling the ladder out this way, then the top of the ladder is going down, which means this y is decreasing. And that decreasing is represented by a negative rate of change. Oops. So part B said, what about when x is 12? So let's do that one now. So when x is 12, we have 12 times dx dt, which is 2, plus y. Well, I need to figure out y again. So I can use the Pythagorean theorem, and I'm going to get that y is 5. So you can check that real quick. Do your Pythagorean theorem with an x of 12 and a z of 13. You'll get a y of 5. So I'll get 5 dy dt equals 0. So this tells me that 5 dy dt is negative 24. So dy dt is negative 24 over 5 feet per second. Okay. So let's do another question that involves some triangles. Let's look at example 6. Okay, so we now have an airplane that is flying at an elevation of 6 miles on a path that will take it directly over a radar station. If the sight distance between the radar station and the plane is decreasing at 400 miles per hour when s is 10 miles, what is the velocity of the plane? So let's definitely draw a picture to get a feel for what's happening here. So we have a plane flying in the air. So here's some bad art. So here's my plane. There we go. There's my plane flying in the air. And we'll say it's going this way. And it is flying at an elevation of 6 miles on a path that takes it directly over a radar station. So let's make a little tower here on the ground. And it is directly over. So what we're going to do is we're going to draw that. And we know it's an elevation of 6 miles. So this distance right here is 6 miles. It is 6 miles above the ground. And then it says the sight distance between the radar station is decreasing at 400 miles per hour. So that's S is the sight distance directly between them. So we'll call that S. And it's telling us that it's decreasing at a certain way. Okay. Let's get some other labels. Let's call this one X and this one Y, just so we have some variables. And let's talk about what's happening now. Okay, so what do we know? Okay, well, we know that's 6 miles, right? the elevation of 6 miles, and that is a constant. So we know that y is always 6 miles here. What else do we know? The sight distance is decreasing at 400 miles per hour when s is 10 miles. Okay. So the sight distance ds dt, that's how s is changing, is decreasing. So we'll just find it as negative 400 miles per hour. And that's when s is 10 miles. We want to know what is the velocity. So step 3, what do we want to know? What is the velocity of the plane? So that was our blue. What is the velocity when s is 10? We'll kind of highlight that too. So what is I'll leave that blank for just a second, d something dt when s is 10? Okay, so what could we think about what is our velocity if we look at this? Well, velocity is how your distance is changing with respect to time. So if we look at here, over here, here is the flight path and its distance is x, right? So its velocity would be how is x changing? How is this distance changing with respect to time? So the velocity is that dx dt. That's what I'm looking for when s equals 10. Okay, so that's our want to know. All right, so step 4, we need an equation. And again, we're going to use our Pythagorean theorem because we have this nice right triangle. And let's think for a minute, what of this is constant and what is changing? Well, I know the plane is flying at 6 miles of elevation. So my y is constant in this case. But now my x and my s, right? The distance here, x, and the distance here, s, those are both changing as the plane flies. So I'm going to make note of that to help me keep up. Okay? All right. So now I need a derivative. So I'll take my derivative. I get 2x dx dt plus 2y dy dt is 2s ds dt. But I know that dy dt has to be 0 because y is not changing. So I can make my equation a little bit easier and say this is 2x dx dt equals 2s ds dt. And I can even go one step further because everything has a 2. They can cancel. And I have that x dx dt equals s ds dt. Okay. All right. So step 6, we can plug in. All right. So what is x? Oh, that's something I don't know yet. If I start all the way here on the left of my equation, I need to start with x. That's something I don't know. But what do I know? The instant I care about, the x that I care about, I know that the y is 6 and my s is 10. So I can come up over here. If s is 10 and y equals 6, that implies x equals, and I would use the Pythagorean theorem with s is 10, y is 6. I'm going to get an x of 8. Okay, so just do your Pythagorean theorem real quick and check that. All right, so let's go back to plugging in. I'll start with x, so that's 8. dx dt, well, that's what I'm looking for, so I need to leave it as dx dt, equals s. My s I care about is 10. That's the moment in time. And what is ds dt? ds dt is negative 400. All right, so this tells me that dx dt is 10 times negative 400 over 8. And we can simplify that. It ends up being negative 500 miles per hour. Okay. All right. Does that make sense that it's negative? Okay. Let's look at what we're looking at. How is x changing? X will be, if the plane is moving this direction towards passing over the tower, then yes, that X value, that distance here is changing and getting smaller. It is decreasing. So it's negative. So this is velocity. That negative tells us direction, but this is decreasing, and the 500 is the speed. So it's flying at 500 miles per hour, but this distance is decreasing.